All right, so let me quickly try this again. We may have lost the first few moments, so quickly, here's the quick review. I apologize, we'll do this at warp speed. This is box of Pigeonhole principles is the following. If we have n plus 1 pigeons p and we have n boxes, okay, so we will color each pigeon one of the colors from 1 through n, equivalent to the boxes. If each pigeon has to go into one and only one box, then there must be at least one box that has at least 2 pigeons. So the first problem we're trying to do it as an example is we considered a set S, which was a subset of 1, 2, all the way up to 2n. We have S having at least n plus 1 elements, and the goal is to show that there exists at least 2 numbers a and b in S where a divides b. So whenever you do a pigeonhole problem, you want to find out what are the pigeons, what are the boxes. There were great comments made in class about this. The first thing is to identify the pigeons, probably elements of S. The boxes, it's much harder. So to try to get a sense of what the boxes should be, we decided, let's try to explore what happens for sets where maybe we don't have enough elements. So we first showed that if this holds when there's n plus 1 elements, it will clearly hold if there's n plus 2 elements. We can just forget about an element. So it's sufficient to consider just the case when S equals n plus 1. All right, well, if we have that, we want to try to find a subset of S of size smaller than this, of size n, where the condition is, where the conclusion fails. And so we had this great suggestion to take the numbers n plus 1 all the way up to 2n. Here's n objects. None of them divide any other. But we want to really milk this and see what can we get. So to go further, we decided, let's consider some number that is not in this set. And it turns out it doesn't matter what number we put in. And the claim was that if we add an x, we know that 2x will be in T. Is that true? That may be false.
I had a question on the premise. At the very beginning, we say that we're looking for an A that divides B, and they're both in S. But doesn't 1 just divide every element of the set?
So we better well make sure we don't include 1 ever.
Yeah. Okay.
So we can't have 1. So it was claimed that if we add in the number x, then 2x is going to be in T. Is that always the case? So can you give me an example where twice x is not in the set? Yes?
If your x happens to be like n over 4, then twice of n over 4 is still only n over 2, and that it divides 2n, but it's not in the set.
Good. But, okay, so the problem is it may not be just a power of 2. Maybe it could be a power of 4, or maybe a power of 3. So we know that if we add in an element x, some multiple of it will divide. So the question is, can you prove that it always has to be a multiple of 2 that divides? So let's think about how much we can jump. So here's 2n, here's n plus 1, here's n, here's our number 1. We keep doubling our number. So let's say we choose some number x. Then we look at 2x, then 4x, then 8x. If we're less than n plus 1, if we multiply by 2, could we go from being less than n plus 1 to greater than 2n? No, so as we keep taking multiples, at least 1 power of 2 is going to have to land in here. And this is the key observation. So some power of 2 times my number x will be in the set. So if we say 2 to the x is in T, that's false. But what is true is 2 to the k times x is in T for some k. So this is giving us an idea of what pigeons to try to find. I'm sorry, what boxes to try to find. Okay. Are there any other sets we can think of that would work, that would have size n plus, that would have size n, where we do not have A divide B? And there's a set that almost works, but there was a comment from class that says why this does not work. So one thing is we looked at the elements from n plus 1 to 2n. That was a great set to look at. Looking at a couple of sets might give us a sense of what's going on. Can you think of any other set of size n where either this condition does not hold or it just barely holds because of the damn number 1?
Like
Yes?
take all other
pick all the odds. Right? So that's almost a beautiful solution. Right? What's the problem with picking all the odds? I'm sorry? Yeah, which divisor do you get? You get 1. So if we try 1, 3, 5, 2n plus 1, arg, 1 divides. There's other issues as well. Could we get around the 1 divides? What could we replace 1 with? 2. 2, 3, 5, 7, 2n plus 1. Now we have all the odds. We fixed the 1. 2 clearly won't divide anything else. But what's the problem? Yes?
3 and 9.
So 3 divides 9, 3 divides 15. Lots of problems. The odds is a great thing to try. Could we try just the evens? No. So with a problem like this, you want to play with a little bit and try to get a sense of what are the difficulties. And so we've got a bunch of examples here. I think this was the best. And when we explored this one, we saw that if the size of t equals n, if we try to add one more number, then some power of 2 times that is going to be in the set. So now we need to try to identify what are the boxes. And we need to end up with n boxes. So anybody have any thoughts about what the n boxes should be? It is related to this, and it is related to this idea here with the odds. Yes?
Is it like divisibility?
It is related to divisibility. Yes?
Could you make the boxes, like, the boxes, okay, so you have your boxes, n boxes, and the first box has n plus 1, and then the second box has n plus 2, all the way up to 2n. And then you still have to place the other numbers in there?
I think that's a little bit too complicated for the boxes.
Okay.
Yes?
Like you want numbers that don't divide into each other.
You want numbers that don't divide into each other.
Every box represents like a divisible by some value. And so if you could, you can show, you can try to put, you can try to get, you have n boxes.
Right.
And you have n plus 1, like no one's to put it in there, and we find out that you have to put at least 2 elements in one box to be that they were both divisible.
Okay, so let me rephrase what you're saying. I want to have my boxes such that everything in this box, something divides something higher in that box. So basically the boxes are going to be ordered. The first one divides the second one divides the third one divides the fourth one divides the fifth one. So if I have boxes like that, as soon as I have 2 things in a box, I win. So again, the difficulty here is trying to figure out how do we want to create the boxes. If I tell you the boxes, it's not hard. This is significantly more challenging than doing proofs by induction. When we're trying to do proofs by induction, we often know what we're inducting on, we often know what we're trying to prove. And so when we're trying to prove that, it's a huge advantage. So we want boxes such that we have maybe x1 less than x2 less than xk, and x1 divides x2, x2 divides x3, dot, 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 xk minus 1 divides xk. And of course, if I write it like that, if x1 divides x2 and x2 divides x3, x1 divides x3. So sometimes people write this as x1 divides x2 divides x3, dot, 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 divides xk. Do all boxes have to have the same number of elements? No. So boxes can be differently sized. So I now want to have a box such that I can easily tell that one number divides everything else. What's the simplest box to think of? 1, okay. I asked for that. Yes, everything. But I want the box to have many elements. So which should I put in next? 2. What should I put in next? 4. What should I put in next? 8, 16, dot, dot, dot. So this is my first box. For my second box, what should I put in? Now what comes next? 6. 2 times 3. What comes next? Not 3 times 3. Because if I put in 9, does 6 divide 9? I'm sorry? 4. So look, I have 1, 2, 4, 8, 16. I just multiply everything by 3. 3, 2 times 3, 4 times 3, 8 times 3, 16 times 3, ... What's the next box going to be? So I've seen several people do it. 5, 2 times 5, 4 times 5, 8 times 5, ... When I have my boxes like this, you give me 2 elements in a box. And I have to have one element dividing the other. So what I'm really doing is I'm writing my number as some power of 2 times an odd number. Is there any number that could be in 2 different boxes? So no number is going to be in multiple boxes. So let's take a number like 15. Is 15 going to be in the 3 box? No. Is 15 going to be in the 5 box? No. It will be in the 15 box. So all of these boxes, it's going to be a partition. So now we have our n boxes. What are the boxes? So the boxes of the form 2 to the k times 2m plus 1. K goes from 1 to whatever. Or I guess 0 to whatever. And whatever will be a function of my odd number. So depending on how large my odd number is, I can take different values for how high k can be. Which is not surprising. The smaller odd number I take, the harder it's going to be. I'm sorry, the smaller odd number I take, the more k I can get and still be at most 2n. So now I have my boxes. How many boxes do I have? I have n boxes. Why do I have n boxes? Each odd number starts a box. So we have n boxes, 1 for each odd number. If the cardinality of S is equal to n plus 1, one box has 2 elements, and we're done. And so that would finish the proof. So this is, in my mind, one of the harder pigeonhole principle problems. I want to start with the hard one where it's not clear how to do it. The hardest part about these problems is identifying what are the pigeons, what are the boxes. This is an extremely powerful method. There's a lot of things you can prove with this. I may give you a link to part of my class in advanced analysis this year, where we use the pigeonhole principle to talk about how well you can approximate irrational numbers with rational numbers. So there's some really important applications of this. Okay, any questions about this? All right, so what I want to do now is I want to go to an easier problem. And I'm hoping now that we've done pigeonhole up the wazoo, the smaller one will not be as bad. So I wrote down a bunch of different ones. So let's do this one. So S is a subset of 1 to 100. S has at least, I think, 55 elements. And now we want to prove there exists A, B, and S such that A minus B equals 10. Okay, which numbers do you think matter? Which numbers do you think don't matter? Or which numbers do you think depend on each other? So there's not that many numbers in this problem. So what numbers do we have in this problem? Yes?
Well, 55 and 100 are related, similar to our previous problem. And I think what we will add is the 10.
So the question is it clear how the 10 is related to 100? Is it the square root? Is it 1/10? How is the 55 related to 100? It's a little bit more than a half. Would this hold for 54 as well? So, again, when you have problems like this, you want to start asking, what are the relationships between the numbers? So step 1, ponder the numbers. All right, step 2, look at smaller sets. You don't need to do step 2. You can jump and try to solve it immediately. I think it's worthwhile to try to look at the structure of sets that have too few elements and try to see what kind of failures do you get. And then try to analyze that failure to figure out what property must be satisfied in the set that works. So in the previous problem, we saw that there must be this powers of 2. So over here, how many elements do you think we should consider? $54. So there might be a way to do it with 54 numbers. So let's try to do it. So here's 100, here's 1. Start giving me some numbers to put in my set. 1 through 10. So I have all these numbers. What's the next number I should add? Okay. I want to avoid having a difference of 10. Don't put 11 through 20. So then I'll do 21 up to 30. So how many numbers do I get here? I'll get another group of 10. So I have 10 here. I have 10 here. I don't have 30 to 39. I then have 41 to 50, and that gives me another 10. I don't have 51 to 60. I have 61 to 70. That gives me another 10. I don't have 71 to 80. And so now what do I have? I now have 81 to 90. $10, $20, $30, $40, $50. That's 50 numbers.
Well, you don't want to have 90.
I don't want to have 90?
If we
We don't have 100 yet.
That's just where 100 is.
Right, that's where 100 is. So can I add any more numbers? So then the question becomes, could I maybe help things along a little bit by dropping one of the numbers here and adding some other numbers? So if I dropped 10, I could add 20, but then I have trouble over there. So maybe I can only do 50 numbers. Maybe 55, they're just having fun with us. At this point, I'm not convinced that we really need 55 elements. I'm not convinced that 54 is doable. So when I write problems, I try to do something like that to give you a little bit more information than you need, just so you don't necessarily know. Also, of course, I have the at least, so we can replace that with has. Because if you can show that it's true with 55 elements, then the other stuff doesn't really matter. What do you think the pigeons will be for this problem? Yes?
Like pairs of numbers that different.
I don't think that would be the pigeons.
Oh,
The pigeons. The elements of S. So the elements of S should be our pigeons, right? So usually in these problems, the pigeons aren't too hard to identify. Let S have this many elements. Okay, well, there's my pigeons. The boxes is a bit harder. So let's try pigeons, the elements of S. Okay. Now let's look at this. How many pigeons are there? There's 55. So how many boxes can I have? So how many boxes can I have? At most 54. So can have at most 54 boxes. What do you think the boxes should be?
One plus 10, 1 plus 10 plus 10, 2 plus 10.
Okay, so you're saying one box should be 1, 11, and 21?
And then all the way to 91. You make 2 arguments.
Ah, double pigeon. Okay, so then we would have 2, 12, I'm sorry?
Can't you have like 1 and 91, and then 91 minus 1 is 90?
I'm not saying it's a multiple of 10, I'm saying it's exactly 10.
Yeah, that's what I'm saying. Like, that would not work. So if you had 2 pigeons in that one box.
Oh, correct. But there's a stronger version of the pigeonhole principle. This is the super pigeonhole principle. All right, at least one box must have the average number of pigeons in it. So now imagine, we talked briefly about this. You put in 4n plus 1 pigeons in your pigeonhole gun, and you shoot 4n plus 1 pigeons into n boxes. One box must have at least how many pigeons? I get 5. Because if you have 4n plus 1 pigeons, the average number of pigeons per box is 4 plus 1 over n. So because the number of pigeons must be an integer, at least one box must have at least 4 plus 1 over n pigeons, so it must have at least 5 pigeons. So what the suggestion is here is to do a double pigeonhole argument. Have one of these boxes having too many things. I'm sorry? The nested pigeons? Oh, I see. I can kind of draw, I think, something like that. All right. So the other possibility is we could look at 1 and 11. We could look at 2 and 12, 3 and 13. The problem with that is how many boxes would we have? So if we tried 1 and 11, 2 and 12, 3, 11 and 21, how many boxes would we have? Yeah, around 90. Maybe it's 89, maybe it's 91. We'd have a lot of boxes, far more than the pigeonhole would tell us. But we would have a lot of the same numbers occurring in multiple boxes. What else could we try? Yes?
Couldn't you then try making the elements like 2 times 55 minus 2 because 1 and 100 would only be added once? So like you had, since you have 55 elements.
Right.
If you say like both, like well, one of the elements is 1, one of the elements is 100, minimize it, then you have fill 2 boxes with those 2, and then the rest of the 53 elements will have to go in 2 boxes each. It doesn't work, but I don't know why.
I mean, maybe I'm misinterpreting it, but maybe you could do here's 1, here's 100, here's the halfway point. At least one of these must have 23. And maybe keep trying to play a game like that. But you might have the problem is it might go across. The set of boxes?
And you say that 53 of the elements go in 2 boxes each.
Right.
And then 2 of the elements just are gone in 100. Then you'll like also break the pigeonhole principle.
Right, but I think that's going to be hard to work with. We could also try to do things like 1, 11, 21. And then the only trouble would be is if you got 2 pigeons in that, if they were the extremes, then you wouldn't be differing by 10, you'd be differing by 20. And so as we start to play this, we start to realize we just have too many boxes. There's just too many boxes going on. So we need to somehow winnow to have the number of boxes become reasonable. And so here, when we do something like this, we have too many boxes. If we tried instead of something like this, if we tried instead 1, 11, 21, we still have too many boxes. But notice we're beginning to move towards here, where the idea is we want to have boxes that are now sufficiently large, and then the idea will be we have so many things in the box that we're going to win. How many things do we need in this box before we win? 6. So let's see. I don't know if it's as large as 6. So let's write all the numbers out. 21, 31, 41, 51, 61, 71, 81, 91. So the worst case is if I have either 1, 2, 3, 4, 5. Yep, you're right, 6. So we need 6 elements before we're guaranteed to win.
Will you just explain that one?
Sure. So if I start off with 1, skip 11, have 21, skip 31, have 41, I basically want to say I want 2 numbers to be next to each other. How many ways can I put numbers down such that I don't have numbers next to each other? Because as soon as they're next to each other, we win. And so if I don't have 1, it makes things even worse. So the best thing for me is I start off with 1, and then I don't have 11. And then I have 21, then I don't have. So that's the maximum ways I can put things in. And so if I climb like that, that's going to take 5 elements. And if I put in a 6th, we win. So as long as we can prove at least one of these boxes has 6 pigeons, we win. How many boxes do we have? We go all the way down to 9, 19, 99. We also have 10. All right. So how many boxes? 10 boxes. Okay, and how many pigeons? 55 pigeons. So the average number of pigeons per box is what? 5.5. What can you conclude? So therefore, at least 1 has 6. And that's what we wanted. As an aside, does anybody remember the Sesame Street character who loves pigeons? Curious about people's Sesame Street knowledge. I'm sorry? No. He likes counting, so he'll like counting pigeons, but it's Bert. Bert loves pigeons. Do you think the 55 can be lowered? Anything above 50. Could it be 50? No. So here when they gave 55, whoever wrote this problem, they did a really good job. Because they gave something that's a little bit misleading. And the 55 was not the critical threshold. The critical threshold was 50. So if I increased 100 to 1,000, see, this is an arbitrary number. I could keep it at 100, and I could replace 10 with 20. And then I could ask, if I keep this at 100 and I replace this with 20, what does that number have to be? So you have 3 numbers here. 2 of them should determine the third. It makes sense that the larger this number is, do you expect you'll need more or fewer elements? What do you expect, more or fewer elements? I would expect more. But this is a good thing to go home and try. Redo this problem and replace 10 with 20. See what you get. Try to do it in general case. You have a set of size n. It might be very nice that 10 divides 100. That might not be a coincidence here. We have an exact number of full boxes. We could have, this partially pigeoned box. It's not the same length as all the others. And if we happen to have a lot of pigeons in that box, that's great. but it could cause some problems. So again, there's a lot of good stuff in these problems in terms of trying to figure out how to extract the way to argue about these. I find pigeonhole arguments very difficult on exams and on contests. I find induction a lot easier. Frequently you have an idea of what to induct on. You have a recurrence relation in front of you. They try very hard to hide what the boxes are. They can't really hide the pigeons. I give you a set S of size 55. Okay, here's my pigeons. But when you look at it, it is not clear what the argument, what the boxes should be. And you start playing. The best thing I know is to just play with the math. Do some examples. Get a sense of what's going on and where things break down. And when you start doing this, you start to realize, hey, wait a minute. We found a counterexample maybe where here's 50 elements and I can't put in a 51st. This doesn't mean, however, that 55 needs to be lowered. Maybe, okay, if we choose these numbers, there's no way, but maybe there's a more clever way. That's always the danger, is could there be a clever idea that you're missing? Maybe 55 is correct, and maybe this is just not the best way. Maybe it's better to skip a little bit. It doesn't seem likely. It seems like this is the best we can do. And as a nice exercise, try to prove that this is the best you can do. All right. I think we have time to state one more problem, but not to do it. So any questions about this before I erase it? So for Wednesday's class, I'll give you some stuff to read about countable and uncountable sets. How many of you have not seen countable, uncountable? Has everyone seen countable, uncountable? Excellent. All right. If you are afraid and do not want to admit in public that you have not seen countable, uncountable, just send me a private email. Okay? Because that will affect how I choose to do the lecture. But there's a lot of very fun problems you can do with countable, uncountable sets and magic wands. And so I will bring one of those. I will see if Caleb will let me borrow one of her wands. If not, Cameron is often a little bit nicer with sometimes for things like that. He doesn't really care about his wand. Well, actually, can probably do it with a sword, I think. Would I get into trouble for bringing a sword to class? Let's find out. Okay, thou shalt not call security or public safety and have them waiting for class. Although this is being recorded. All right, so A1, A2, AN are positive integers. Let's say distinct. And I think I want to subset that, yes. Well, actually, I'll even get rid of it. I don't think you need distinct. Show there is a subset that sums to a multiple of n. What do you think might be useful for this? Pigeonhole. Why? We've just covered Pigeonhole. I said we're running out of time. But maybe I'm doing this to mislead you. If Pigeonhole doesn't work, what might work? So does this look like a problem? When you look at this, does this feel like this is a problem I want to do induction on? Why not? Yes?
There's no clear way to get from n to n.
There's no clear way, so I'm going from multiple of n to multiple of n plus 1. So you want to get to the point where you can start to recognize which techniques might or might not be useful. This does not feel like an induction problem. I might want to induct on sizes of subsets, maybe. But this is a good one to think about. Why do I say multiple of n and not just sum to n?
Consider the set with just like the number 7 in it.
Or better yet, all of my numbers are 5n. So I mean, if my numbers are really large, then it's clearly not going to sum to n if every number is greater than n. So in problems like this, you always want to standardize and see what's the right way to look at it. Can I assume my numbers live between 0 and n minus 1 or between 1 and n? Can I make that kind of simplification? if my number is equal to 4n plus 8, well, when I'm looking at the sums, I want to get a multiple of n. The fact that it's 4n plus 8, the 4n doesn't really matter. It's just along for the ride. So I can always just tweak this and say, screw it. Let's assume my numbers are between 0 and n minus 1, or between 1 and n, whichever you're more comfortable with. And then you can start to think, does it matter if they're distinct or not distinct? And then we want to show that there's a subset that sums to a multiple of n. What do you think you might want to try to do to get a contradiction? What might you change a little bit? N minus 1. So imagine now you have only n minus 1 objects. Can you choose n minus 1 objects so that no subset sums to n? And then what goes wrong? So again, if you're going to do this with the pigeonhole principle, what must you do? Step 1, identify the pigeons. This is like Alcoholics Anonymous, right? And if you want to do it anonymously, you can use the Eve's Math account, right? Identify the pigeons. Step 2, boxes, okay? All right? If you're not over 21, then don't worry about Alcoholics Anonymous, okay? All right? So try to see if you can do this for...
Reason to worry if you were below 21.
No, because if you're under 21, you haven't drunk.
I know, so that's why it would be a worry.
Oh, that would be a worry? No. Okay, so this should be plenty of stuff to do. I will send you some reading to do about uncountable and countable sets. Those become really nice things to use for a bunch of contest problems. It also leads into some really good notions of mathematics, and I want to use this class as a springboard. All right.